My name is Mara Freilich, and I'm a PhD student in the MIT Woods Hole Oceanographic Institution Joint Program. I'll be talking about the pathways connecting the ocean surface mixed layer to the ocean interior. The properties of the ocean interior are set by exchange at the sea surface. For example, oxygen enters the ocean at the sea surface and is consumed once a water mass leaves the surface and loses contact with the atmosphere. Primary production, which fixes carbon, also happens in the upper ocean. And so the transport of water masses across the stratified base of the mixed layer ventilates the ocean interior, resupplying oxygen and sequestering carbon. Unraveling the dynamical pathways that connect the mixed layer and the interior will help us to better understand ocean biogeochemical cycling. The mixed layer is weakly stratified and has low potential vorticity, or PV, because of atmospheric forcing. The interior is more stratified and has high PV. Here, we focus on the dynamics that transport water parcels across the mixed layer base and into the interior. We take a Lagrangian approach and characterize the trajectories of water parcels as they move along sloping isopycnal surfaces and into the interior. We ask, what are the mechanisms of submesoscale subduction from the mixed layer in the context of a strong mesoscale front? So where we have isopycnal surfaces that are outcropping at the surface. Here, we're using submesoscale to mean both small spatial scale, so in the order of 1 to 10 kilometers, and in the dynamical sense, meaning that relative vorticity is large and geostrophic effects become important. Our hypothesis is that along front variability and the frontogenesis processes that act on that along front variability drive subduction out of the mixed layer. To test this hypothesis, I will use a process study model initialized with the upper ocean density structure from transects in the western Mediterranean Sea. And we'll return to this location with observations at the end of the talk. The model is a zonally reentrant channel and has a 500-meter horizontal resolution. There's a weak surface cooling and no wind forcing. I seed Lagrangian particles across the domain in the mixed layer in the model and reseed every day and run the particle trajectories for 10 days, which is about the time to transit the full domain. I then identify where particles leave the mixed layer. And so over the 30 days of the experiment, 18,740 particles leave the mixed layer. And that gives us good statistics on these dynamics. Here, though, I'm showing surface snapshots, plots of the surface density field from 3 days. The shaded dots show the location where water parcels left the mixed layer on each day of the experiment. And the shading shows the relative vorticity on the particles when they left the mixed layer. From this, we can see that subduction is intermittent in space and time, with subduction mostly occurring localized at the strongest fronts, but only intermittently along those fronts. And the vast majority of the subducting water parcels have cyclonic vorticity, and many have vorticity order F, order Coriolis frequency. And so in 3 dimensions, we can track water parcels as they leave the mixed layer. And so here I'm showing a density surface in 3D. The density surface is shaded with relative vorticity. And the black dots are water parcels that were initially in the mixed layer and are now subducting out of the mixed layer. So some of these water parcels stay very close to the mixed layer depth even as they subduct, while others are subducting in small scale features down to 80 meters. Now we'll discuss how these water parcels are leaving the mixed layer by tracing dynamical properties. In these plots, all of the water parcel trajectories are composited on a shifted time axis, where time 0 is when a water parcel subducts. The solid line is the average across all trajectories, and the shading shows the interquartile range, the average or interquartile range of each of the properties. And so the left-hand panel, I'm showing stratification, And as expected, stratification increases dramatically as the water parcel leaves the weakly stratified mixed layer and enters the pycnocline. And then on the right-hand side, I'm showing vertical velocity. And consistent with expectations as well, vertical velocity, which is 0 at the surface, increases as water parcels subduct. And then when the subduction is done, so subduction in each of these cases persists on average for just a few days, the vertical velocity decreases again. And in the lead up to subduction, we see that the lateral buoyancy gradient increases on particles. So the Lagrangian rate of change of the lateral buoyancy gradient is the frontogenetic tendency. And so from this we learned that subduction is tightly linked to frontogenesis. We also find that the cyclonic vorticity peaks immediately prior to subduction, reaching order F on the upper quartile of trajectories. And we also, by looking at the relationship between cyclonic vorticity and the vertical velocity, particularly the vertical gradient of the vertical velocity, we see that the increase in vorticity is consistent with vortex stretching, dominating the change in the relative vorticity at the surface. And so to better understand the subduction mechanisms, we can decompose the frontogenesis into different forcing components. So each of the 5 components are geostrophic frontogenesis, ageostrophic frontogenesis, so straining of the lateral buoyancy gradients by the ageostrophic, horizontal ageostrophic velocities, vertical, which is differential vertical motion acting on buoyancy gradients, horizontal and vertical diffusion. We find that on average, looking at the composite plot again, that the frontogenesis is driven by geostrophic frontogenetic forcing, which is balance straining by the large-scale flow field. However, near the subduction time, there's also frontogenetic contribution on average from the ageostrophic component, but because the ageostrophic term is not frontogenetic on all the trajectories, it makes a small contribution to the average, even when it can be important on particular trajectories. And then on average, frontogenesis is balanced by lateral diffusion and the vertical part of the ageostrophic overturning circulation, which is weakening the isopycnal slope, or restratifying isopycnals. And so despite the geostrophic nature of the average frontogenesis, there's also evidence that ageostrophic effects are important for subduction in this system. So previously, I showed that subduction occurred on features with spatial scales of around tens of kilometers when we were looking at the snapshots of the subduction location. And we find that these features result in spiraling trajectories during subduction, and that ageostrophic acceleration on the trajectories enhances subduction. And when we look at individual features, we also see that ageostrophic effects can dominate. In this example, I'm showing a snapshot from the animation where we saw subducting particles on a isopycnal surface. And here at this dense filament, a submesoscale dense filament, which is also a submesoscale cyclonic filament, if we look at the frontogenetic forcing on these particles from the mixed layer into the interior, we see that both ageostrophic frontogenesis and geostrophic frontogenesis contribute prior to subduction. And so this model helps us to interpret observations. So this is a transect now from an observational transect from the Western Mediterranean. We surveyed across the gyres in the Alboran Sea. And so on the left, I'm showing surface chlorophyll, and we see submesoscale features in this chlorophyll image at the strong front. And then at this yellow line, we on board a ship, took a transect of temperature and salinity, and here I'm showing temperature on the right-hand side. And in this transect, we see 2 subduction events from the mixed layer to the interior. And the modeling results can inform our understanding of the spatial and temporal scales of this event. So say that some of this along front variability that we're seeing in the satellite image is likely very important for driving the subduction from the mixed layer into the interior. And so overall, we find that a variety of submesoscale processes influence the rate and pathways of subduction at a strong mesoscale front, which modifies the conductivity between the surface and interior. And we find that subduction occurs in coherent features that have spatial scales of tens of kilometers. And so counter to previous results, we find that submesoscale subduction can occur through either high or low potential vorticity pathways. And this last point in particular, this talk overall, is discussed further in this manuscript below. And if you have any questions, please reach out by email or in the conference chat platform.